but this really works. That is that you can actually take the differentiation operator inside, since f is a constant, you can have the differentiation or derivative operator operating on that function, which is a function of time. So what is the differentiation, the derivative of e to the j omega t, according to what you have learned with Euler's identity? Right? You have to learn this rule. d dt of e to the j omega t is just j omega t e to the j omega t. This is a very important rule. It's so simple. Every time you differentiate an exponential function that is sinusoidal, okay, that's exponential, just bring down the j omega, okay? And you can do this n times. You do it 2 times, you bring j omega squared. If you do it n times, what is the prefactor that you have to add here? J omega to the power of 3, 4, 5, or what? Minus 1. Okay. So I think the smart one will say n. The silly one will say minus 1. Okay? So let's see what we can do. I guess I don't have to derive the details of this, right? All of you can infer this. I don't have to show in great detail that this is true. So if that is true, then it says that the n derivative of the phasor form of a cosinusoidal function is just real part of this times, I can put the j omega here, and f e to the j omega t. This is true. I just replace the nth derivative with j omega to the power of n. So the phasor representation of this function is just equal to that. Okay? That is that if you differentiate a cosinusoidal function n times, its phasor form is just j omega to the n times f. Okay? You have this very simple rule. So let's do example 4.8. 4.8, you have this ODE. Cosine of 4t. What happens to this ODE if I were to write everything in terms of its phasor representation? It becomes actually a very simple equation. Okay, so if I were to let f be the real part of f e to the j omega t, if I were to substitute this into the first equation, the first term, I would have real part of the first term would be just j omega f e to the j omega t. Okay, and then the second term would be 4f e to the j omega t. And then the right hand side would just be 2 times the real part of e to the j4t, right? And in order for these two equations to match up, what must I pick for the omega on the left-hand side? Must be 4. Otherwise, this equation can never match. Okay? So if I pick omega to be 4, then the left-hand side looks like the right-hand side. Okay? And again, if I take, let me combine these two first. I combine this into a form that's j omega f plus 4f e to the j omega t equal to what I have on the right hand side, real part of 2 e to the j4t. Okay? So, what you have here is a very simple example of solving an ODE with phasors. Okay? First, this equation cannot be satisfied unless the left-hand side, the f, responds with the same frequency. If you were to drive an equation with the omega equals to 4, the particular solution must respond with the same frequency. We found that many times over before we went into phasor, but here you see it to be very clear immediately, right? You see it to be very clear immediately. And then you have to take this real part of these two functions for all times. This has to be valid for all times. This number is going to go round and round and round on the complex plane, right? So if this is going to be obeyed for all time, then this part must be equal to that part. Okay? So because of that, you argue that the equation I have must be that j omega f plus 4f must be equal to 2, and omega must be equal to 4 in order for that equation to be satisfied. But look at how simple this equation is. A very complicated ODEs just become an algebraic equation. You solve an algebraic equation to get the phasor. So this is purely algebraic. And f is equal to 2 over j omega plus 4, where omega is equal to 4. You can solve for f quite easily. And f is the particular solution. Okay, and we know that the particular solution to this equation is cosinusoidal. Okay, so this is one use of the phasor form to solve an ODE. And let's try another example, example 4.8. 4.8 is done, so let's do example 4.9. We have some time left. I think I have some time left. Okay. So, example 4.9. I have partial square y partial t squared plus 3 partial y partial t plus 2y is equal to 5 sine 6t. Okay? Let me let y be equal to the real part of y e to the j omega t. Okay? What must omega be? First rule number 1, omega must be 6. Okay? And then that second order ODE will be converted into an algebraic equation in phasor form. Okay? You can go through the mathematics, but now you actually can do it by inspection. Second derivative introduces what? J omega square, right? Times that phasor plus 3. First derivative is j omega times that phasor plus 2 times that phasor. And then write the phasor form on the right hand side, which is minus 5j. So this is the phasor form of the second order ODE. It becomes algebraic. You can solve for your y. You put omega equals 6. And you can do all the complex arithmetic of complex numbers. Yes?
Why do you have negative j omega squared?
Where did they get? Oh, sorry. This should be plus. Okay. Because the world is very different. Some people use e to the minus j omega t. In the physics department, they always use e to the minus I omega t. Okay, so I just forget that. I'm not talking to physics students. I'm talking to electrical engineers. So I should have plus j omega. Okay? Very good for pointing that out, and very good for catching that. Actually, the square would have removed the minus sign, but I don't have an excuse. Okay, to put thing in a minus sign here. But you solve this, and then you get your y. I won't do the details, okay? And then you have things like Kirchhoff current law. I1t plus I2t plus say I3t is equal to 0. If I write this in phasor form, it will be real part of I1 plus I2 plus I3 e to the j omega t must be equal to 0. And this thing is going round and round in the complex plane for all t. So I can remove this and say that if this has to be 0, I must have I1, I2 plus I3 is equal to 0. So Kirchhoff current law becomes like that. You just add the phasors together. And similarly, this is KCL. You can also do KVL for a loop. Okay, V1 plus V2 plus V3 plus Vn must be 0. Okay, you can do the kind of arguments. All the Kirchhoff current law and the Kirchhoff voltage law will become just the same in the real world or the phasor world. And that makes things very simple. You can apply Kirchhoff voltage law and Kirchhoff current law even in the phasor world. Okay? So, let me talk about the last example in the textbook, which is example 4.10. So, if I have Vt is equal to L di dt for an inductor, then in the phasor world, this just becomes J omega Li. Okay, can everybody see that? I just have to replace ddt with J omega. Okay, I get this very simple relationship. So no more derivative operators, just a algebraic relationship. V and I are related very simply by a complex number. And then you have the other law, the other IV relationship of capacitors. And then in the phasor world, this is just equal to that. Okay, you want me to go through the detail? I don't have time for the detail, but if you don't believe me, go home and try it out. Okay, do the details. So, and then for resistors, you have Vt equals to Rit, and it remains the same in the phasor world. This is just V is equal to Ri. Okay. So you can have this been written as V equals to Z times I for an inductor. And you can call that the impedance of an inductor is J omega L. Okay, you can write this as I is equal to admittance. Admittance is 1 over the impedance times V. Okay, the admittance of a capacitor is J omega C. And then the resistance of a resistor is just R. Okay, have you learned the concept of impedance and admittance? No, right? So in the phasor world, you generalize this relationship to a complex number. Instead of V equals IR, now V is I times Z, where Z can be a complex number now. And that Z is equal to J omega L for an inductor. And that Z, if I write this in terms of Z, that Z is just 1 over J omega C for a capacitor. Okay? And I guess all of you are in a hurry to leave. I'll let you go.